we are going to study about principal component analysis. Tata. In this lecture, we are going to study about principal component analysis, one of the most important concept in machine learning. We will be talking a lot about PCA or principal component analysis in machine learning. Whenever you study ML, any research article related to machine learning or any algorithm you are trying to solve, you will talk about PCA. PCA is linked with the most important concept, that is dimensionality reduction. So, before we understand PCA, let us understand what is dimensionality reduction. We will go back to our basics of machine learning. The heart of machine learning is data. So, when you have data, using the data you can build ML models. With those ML models can help us in either classifying or even prediction. Basic task like doing prediction of something or doing classification of the data, right. All this is possible only when you have some historical data, only when you have some real data with us, right. So, you have data with you. Now, when you want to visualize the data, when you want to play with that data, if the data is in single dimension or in two dimensional format, it is very easy. What if the data is in large size? And obviously, ML data will definitely be in larger size. You will have at least, maybe let us say there are 1000 columns of 1 lakh students. I have 1000 details of 1 lakh students. It is a very huge data set. Can you imagine how big the data is? Can you visualize and see how is the data distributed? It is not possible, right. In 1000 dimensions I cannot visualize it. Okay. So, in that case we have to do an important concept, we have to apply one important concept called dimensionality reduction. So, what is this dimensionality reduction? Dimensionality reduction is the process of reducing the number of input variables in a data set while preserving the essential information. So, when I have the data of students, let us say I have data of some 1000 students, okay, and for those 1000 students, I have their name, their first name, their last name, their surname, let us say date of birth, I have the semester they are studying, right, what marks they have got in subjects and so on. So, among all these data, suppose I want to derive an insight, I want to find out students who are good at mathematics, are they getting placements or not? Or I want to find out something, is there any relation between students having high marks in mathematics, high in mathematics are getting high packages. Okay. So, I want to derive such kind of insights, I want to find out such kind of insights. To do that, is this whole data required for me? Is there anything, any significance or any relation with his marks in, let us say in some electronic subjects? A computer science student studying, he has to study lot of courses. In that there are mathematics courses, there are electronics courses, some communication courses and so on, right. Some MBA courses, we study lot of courses. Among all those courses, I want to find out if a student is good at mathematics, is he getting a good package or not. So, in that case remaining features are not required, all these are the features, we do not need all these features. Okay. So, dimensionality reduction is a process where we actually try to reduce the number of feature variables, number of input variables, right. So, by doing that it becomes very easy for us to do some computation, find out some insight from that, visualize the data and see how is the data distributed, lot of other things are involved, right. So, if you see here, there is a large table with lot of observations, I am trying to reduce them into a small set of with only few columns, right. The most important point, we are preserving the information as much as possible, we are not deleting them, we are only identifying which are the most important columns for this problem. What is the problem here? Find out the insight, find out the relation between the student getting good marks in mathematics and getting high package, right. So, that is what dimensionality reduction is, we try to reduce the number of features. Now, why we have to do dimensionality reduction? What is the benefit of that? Right? When you reduce the dimension of the data, we have smaller data sets. We have smaller data sets. It becomes very easy for us to visualize the data. If you want to plot some graphs, see how is the data distributed, find out what is the maximum value, what is the minimum value, lot of things you can do using visualization. it becomes very easy. When you visualize the data, you understand the data much better. That is why we have to apply dimensionality reduction, right. This is one of the easy approach of doing it, and it sometimes, see in this example, if you see, I have customer age, account age, days since login, right. If I can reduce something here, I am actually losing the information. I cannot delete any of the columns here. I cannot do dimensionality reduction here because it is very small data, right. When you only have larger dimension data, then you have to identify which are the most important features and try to eliminate or delete or do some operations, right. Project that data into some other column so that you have less number of features, and it becomes very easy for us to visualize the data, right. So, dimensionality reduction is important to, if you have a smaller data size, if you have smaller data sets, it becomes very easy for us to visualize the data, right. Next, what are the different techniques of dimensionality reductions? How can we do this? Given a data set, how can I reduce the dimension of the data set? There are multiple approaches of doing it. So, one among them is the principal component analysis. What is principal component analysis? What it does? Actually, it projects the data to new axis that captures maximum variance. So, when you have, let us say, when you have two dimension x and y, you want to compress into only a single dimension x bar, right. So, this data in two dimension x, y, you are trying to project them in a single line where there is maximum variance. Okay. So, this is one technique. The second technique is linear discriminant analysis, LDA, right. So, it projects the data to maximize class separability. Okay. So, what I have to do here? We have to actually, when we have multiple classes of data, we have to cluster them, we have to group them, we have to separate the data, right. So, LDA does that. LDA does in linear discriminant analysis, we project data to maximize the class separability, because data in one view, if you see in one dimension, if you visualize the data, it may seem that 3-4 classes are combined together, but if you just rotate it and observe the data on a plane, then you will see that there are different classes which can be separated. So, that is possible using linear discriminant analysis. And the other one is TSNE, right, T distributed stochastic neighbor embedding, So, again this is used for 2D, 3D visualization. Like this, there are n number of techniques where we can apply to do the dimensionality reduction. So, we are going to study about PCA, that is principal component analysis. We will try to understand mathematically what is PCA and what it does. Also, we will try to solve a numerical problem. So, in PCA, right, what is PCA? Okay. So, it is an unsupervised dimensionality reduction technique. It is a dimensionality reduction technique that transforms the higher dimension data into a lower dimensional space while retaining the maximum possible variance. Okay. See here, see this example diagram here. If you see the example here, right. So, I have a data points in x and y axis spread across x and y axis here. So, I am trying to project all these data. Into a single axis. So, this is 2D, this became 1D, right. So, PCA is a technique, dimensionality reduction technique, that transforms a higher dimension data into lower dimension data, right. So, let us see, suppose you have a 100 feature, you have a data set with 100 feature, right, but many are correlated or redundant or repeated. PCA can reduce it to 10 uncorrelated principal components, 10 uncorrelated principal components. So, we can 1000 features can be reduced to 10. We are not deleting actually, in PCA we are not deleting, we are trying to project these data points, into a single dimension data, right. These data points here are being projected into a single dimension data, that is what PCA does. How it does? Wherever there is maximum variance, right, retaining the maximum possible variance, that we try to do. This is what principal component analysis is. Okay. So, what is the procedure of doing this? Now, let us say somebody has given you the data in 2 dimension, how do you convert into 1 dimension? What is the procedure for that? right. So, for that you have to first standardize the data set, then compute the covariance matrix. After computing covariance matrix, we have to find out the eigenvalue and eigenvector. Whichever eigenvalue is high, its corresponding eigenvectors we will be taking, okay, right. Once you find out the eigenvalues, we compute eigenvectors as well, right. So, whichever eigenvalue is large, for that we try to find out the eigenvector. That eigenvector we will be using to find out the new data in the one dimension space. Okay. If you see the procedure once again, given the data set X of n cross d dimension, we try to standardize the data, we find out the covariance matrix. For that covariance matrix, you find out eigenvalue, then find out eigenvector. Okay. Sort the eigenvectors in decreasing order. So, whichever has highest eigenvalue, that will be on top, that will be the first one. So, if you want to find out principal components, first principal component, you have to take the first eigenvector and then project on the new space. So, with this you can calculate the PCA. Okay. So, in our next lecture, we will try to solve one problem and try to understand how to find out PCA, how do you find out the compressed values. So, given in 2-dimension data, how do you find out the data in a single dimension. Okay. Thank you. In this lecture, we will study how to we will try to solve a problem on principal component analysis. We will try to take a simple problem and try to solve this. So, see the problem here, given the data below, reduce the dimension of the data from 2D to 1D using PCA. Okay. So, we have two features X and Y. So, we were talking about features, right. When you have multiple features F1, F2, so on Fn, our job of dimensionality reduction is to remove or reduce the features from n features. You maybe if n is 10, I want to have only 3 features, So, that is possible using PCA, right. So, we are actually not eliminating we are not deleting the features, but we are trying to project those data into another plane. So, we will try to see how data in XY plane is being reduced into a single dimension data. Okay. So, the problem is given to us, we are given two features X and Y and we are given ABCD as the 4 values, right. So, what is the first step here? First step is we have to compute the mean, compute X bar and Y bar. So, if you find out X bar value, so 4 plus 8 plus 13 plus 7, if you find out, we get mean as 8 and also we get Y bar. If you find out the average of these 4 values, you get it as 8.5. The second step is to construct the covariance matrix. Okay. Calculate the covariance matrix. So, how do we construct the covariance matrix? See here, covariance matrix for 2-dimensional data for X, Y is nothing but covariance of X comma X, covariance of X comma Y, covariance of Y comma X, and it is covariance of Y comma Y. Okay. Covariance of XX, covariance of XY, YX and YY, right. So, let us find out all these 4 covariances first. So, covariance of X comma X. So, what is the formula here? Summation of I equal to 1 to n xi minus x bar whole square by n minus 1. This is the formula for finding out the covariance of a variable. So, xx is nothing but xi minus x bar whole square by n minus 1. So, how do you find out this? So, it is nothing but what is x1? x1 is 4, and x bar is 8. So, it is 4 minus 8 whole square plus 8 minus 8 whole square plus 13 minus 8 whole square plus 7 minus 8 whole square. divided by n. Total number of how many features are, how many values are given to us? 4 data points are given to us. So, it becomes 3, 4 minus 1. So, if you solve this covariance, if you solve this, you get the value as 14. Okay. So, covariance of XX is 14. Same way, find out covariance of YY, covariance of y comma y. So, the formula is summation of I equal to 1 to n yi minus y bar whole square by n minus 1. So, if you solve this, again what is yi? This 11, 4, 5 and 14 are the yi. What is y bar? Y bar is 8.5. Okay. So, if you substitute again here, let us say I have 11 minus 8.5 whole square plus 4 minus 8.5 whole square plus 5 minus 8.5 whole square plus 14 minus 8.5 whole square divided by 3. So, if you find out this value, if you solve this using calculator, you get the value as 23, right. So, you got the covariance of XX as 14, YY as 23. Now, next we have to find out the covariance of XY. See, covariance of XY formula is equal to covariance of YX, both are same. Why? The formula is something like this: I equal to n xi minus x bar into yi minus y bar, right, whole divided by n minus 1. Okay. So, when it is xy, it is xi minus x bar, yi minus y bar by n minus 1. When it is yx, it is yi minus y bar, xi minus x bar by n minus 1. Okay. So, we have this. So, single value can be enough for us to calculate. So, if you calculate this value, you will find it as minus 11. What is xi? I have all the values of x1, x2, x3, x4. I have y1, y2, y3, y4. I know x bar is 8 and y bar is 8.5. So, substitute all this, you get the value as minus 11. So, we got the covariance matrix now. What is the covariance matrix? Covariance matrix M is nothing but we have to we got covariance of XX, XY, YX and YY. We got this as our covariance matrix. So, what is the next step? After finding the covariance matrix, the next step is to find out eigenvalues. Find out eigenvalues. Okay. So, how do you find out eigenvalues? We know A minus delta lambda I equal to determinant of A minus lambda I equal to 0. So, this is our matrix A. So, for this find out the eigenvalues. So, if you do determinant of 14 minus lambda minus 11 minus 11 23 minus lambda. If you find out determinant and equate it to 0, you get some equation as lambda square minus 37 lambda plus 201 equal to 0. So, if you find out the lambda values, if you solve this equation, you get lambda 1 as 30.3 and lambda 2 as 6.6. So, we find out the eigenvalues. Now, we have two eigenvalues because we have 2-dimension data, right. So, whichever is the largest eigenvalue, for that you find out the eigenvector. So, how do you find out eigenvector for eigenvalue, right? You can solve this. There are different ways of solving it. So, in linear algebra, you might have already studied how to find out the eigenvector for a given eigenvalue. So, if you this is the largest one. So, since we are shifting or we are transforming the data from 2D to 1D, right, I will choose only the largest eigenvalue. So, if I find out the eigenvector for lambda 1, we get something like this 11 and minus 16.38. Okay. So, this becomes the eigenvector. Then we have to normalize the eigenvector. So, what is normalization of eigenvector? The next step is to normalize the eigenvector. Okay. What is normalization of eigenvector? What was the vector we got here? 11 and minus 16.38, right. Normalization means you have to find out the magnitude of that first. So, square root of 11 square plus again 11 whole square minus 16.38 whole square. So, you have to divide this. So, normalized eigenvector becomes, right, if you find out this value and then you divide 11 by this. So, it is 11 by square root of 11 square plus minus 16.38 whole square. Same way minus 16.38 divided by square root of 11 square plus minus 16.38 whole square. So, when you solve this, you get the normalized eigenvector as 0.5574 and you get minus 0.8303, right. So, this is the normalized eigenvector. For which one? For the highest eigenvalue. For the highest eigenvalue, that is 30.3, I found out these values. Now, once you get this as the normalized eigenvector, right, now we have to find out the principal components. We have to find out the principal components. Okay. What is PCA? We are trying to find out the first principal components. First principal components. So, if you want second level principal components, you have to go for second eigenvalue. Take second eigenvalue, find out its eigenvectors and normalize it. Okay. So, for me the normalized eigenvectors, I write it here. We got the values as 0.5574 and minus 0.8303. Okay. These are the normalized eigenvectors. So, once you find out this, now you go back to now find out the PCA, the first principal components. First principal components. How do you find out this? So, what is the data given to us? We have A with us, right. For A, how do you find out? It is nothing but vector transpose into x1 minus x bar, y1 minus y bar. This is what we have to multiply, right. So, what is V1 transpose? It is 0.5574 and minus 0.8303 into x1 minus x bar. What is given in the question? If you see, x1 value is given as 4 and x bar we know 4 minus x bar is 8 and y1, what is y1 value given in the question? It is 11 minus the y bar is 8.5. So, you get, if you subtract this, it becomes the same matrix into minus 4 and this is 2.5, okay, minus 4, the same 0.55 and minus 0.83 into this, right. If you multiply this, you get here minus 4.305. So, this is the first value for A. Same way for B, how do you do that? V transpose into x2 minus x bar, y2 minus y bar. So, if you again solve this, you get something around 3.736. For C values, C means the third feature. Now, the third value is what is given to us, x3, y3, you get it is 5.692 and D you get it as minus 5.123. So, if I write the new features, it becomes something like this. Okay. So, for A what it is? It is minus 4.305, for B it is 3.736, for C it is 5.692 and for D it is minus 5.123. So, this is the one dimension data in single dimension. This is your A, B, C and D, right. Let us go back to the question and see what we were given. We are given a 2-dimension data with 2 features x and y, okay, with 2 features x and y. So, x1, x2, y1, y2, x3, x3, y3, x4, y4, right. So, these values are given to us. Using these values, we have computed and reduced the dimension of 2D data into 1D data. So, it is same as we are trying to project that 2D data into a single line and these are the new values. See, we have reduced I have not deleted any components. I have projected the 2D data into a single line. When I project that into a single line, these are the values which I have found out, right. So, this is what we call it as principal component analysis. We try to compress the data, we try to project the data in a higher dimension into lower dimension one. So, in this example, we have seen how a 2-dimension data is projected or compressed to form a single dimension data. So, this is the problem of principal component analysis. What is the procedure of doing it? See, first you have to find out the mean x bar and y bar and then you have to compute the covariance matrix. So, to find out the covariance matrix is nothing but covariance of xx, covariance of xy, yx and covariance of yy, right. So, formula to find out covariance of xx, it is summation of I equal to 1 to n xi minus x bar whole square by n minus 1. N is the number of values given to us. right, number of data given to the, so we are given 4 data points, so we divide it by 3. Same way covariance of yy is nothing but summation of I equal to 1 to n yi minus y bar whole square by n minus 1, right. So, covariance of yx and xy are same, covariance of xy and yx are same, summation of I equal 1 to n xi minus x bar into yi minus y bar by n minus 1. So, once you get the covariance matrix, right, you have to find out the eigen values of the matrix. You got 2 eigen values. In that you choose the highest eigen value, for that you find out the eigenvectors. So, you get the eigenvectors as 11 and minus 16.38. Then try to normalize this. When you normalize this eigenvector, you get this as the value. Okay. After getting the normalized eigenvectors, to find out the components, actual the new data points, to find the new data points for A, it is V transpose into x1 minus x bar into as a matrix, as a vector, x1 minus x bar, y1 minus y bar. So, V transpose this vector transpose into this. So, if you solve this, you get the new value as minus 4.305. Same way if you do for B and C and D, you get this as the values. Okay. So, this is the new data point after compressing the data point from one dimension, 2 dimension to 1 dimension, this is the output we get. So, this is the concept of principal component analysis. Thank you.